All right, for lesson 3, we're going to carry through with our lesson 2 idea. On lesson 2, we talked about parallelograms. Parallelograms is a broad description of quadrilaterals that have two pairs of parallel sides, and we learned about their properties. Today, we're going to be talking about 3 specific types of parallelograms. They are parallelograms, but they each have their own little details that separate them and make them their own type of parallelogram. So everything that we learned previously on day 2 is still going to apply to these shapes. We're just going to have extra little details that make them different from each other. Okay, so a rectangle, the first one we're going to talk about is a parallelogram with 4 congruent angles. Alright, so a rectangle is a parallelogram with 4 congruent angles, and we talked about on day 1, all of the angles inside of a quadrilateral add up to 360, because there are 2 triangles inside. So if all the angles are congruent and they add up to 360, they must be 90 degrees each. I'm sure you guys are familiar with seeing a rectangle with the 90-degree corners. That is related to the official definition of a rectangle. So a rectangle with the 90-degree corners, it is still a parallelogram as part of the definition. So I'm going to write down everything that we're going to know as properties of a rectangle. The first 5 are going to be things that we know previously from a parallelogram. And then number 6 is going to be something that's unique for a rectangle. It is not true for every parallelogram. It's going to be true for rectangles only. So first thing, we know opposite sides. I'm going to abbreviate opposite sides are parallel. That's using the definition of parallelogram. So the fact that a rectangle is a parallelogram follows through to say that opposite sides are parallel. Now, the 4 properties that we learned about a parallelogram besides its definition is that opposite sides are congruent. That was one of the things that we learned to help us solve. We also learned that opposite angles are congruent. We learned that consecutive angles are supplementary. And then we also learned that the diagonals bisect each other. Okay, so everything that we've talked about before for a parallelogram, all those are true. We also know the definition of a parallelogram gives us those 90-degree corners. Now, what else do we know about a rectangle that's different than just a plain old parallelogram? Well, that's going to be number 6 here. The extra property that we know about a rectangle is that the full, in all caps, diagonals are congruent. The full lengths are congruent. So before, in just a run-of-the-mill, overarching, broad description of a parallelogram, all that we knew was this, was that the diagonals bisect each other. And if you remember in the diagram when we saw that picture, when I drew the parallelogram, I had single marks here along this diagonal and double marks along that diagonal, which indicates that the full lengths are not equal in just a plain old parallelogram. Okay? So this is what a parallelogram would look like, just a run-of-the-mill, boring old parallelogram. But once it becomes a rectangle, it is true that the diagonals still bisect each other, but because the full lengths are equal, I don't have to put double marks like I did for the other parallelogram. I can put the same marking for all 4. Because if the full lengths are equal and they're both being cut in half, then all 4 of those segments are going to be congruent. So this picture is the result of property number 5 and property number 6 working together. And this is really important. I want you guys to draw that in your notes. This is really important, something that's helpful with a rectangle. The fact that all 4 of these little segments are equal helps you out because I now have isosceles triangles on the inside. So you do want to remember that because using those isosceles triangles will be really helpful. Like if I was trying to find this angle, right? We don't have any properties about what angle's there where the diagonals crisscross. So using the isosceles triangle, like if you knew this angle, you could use that to help you find that vertex angle of the isosceles triangle. So do keep in mind that working with that property phi, that they bisect each other, and the fact that their full lengths are equal, you can get that relationship. Now this is only true for a rectangle. Remember, for a regular parallelogram, I'll just draw this to compare. We had, and that's super squished. Let me try that again. Right, this was the before. This is just a regular parallelogram. This is a rectangle. Before, we had to say that they were different lengths. For just a regular parallelogram, for a rectangle, this is true. Okay? So this is no longer going to be our situation. Okay. Let's use the properties of a rectangle to help us solve. So if a property of a rectangle does not immediately apply, you guys do want to see if any triangles inside of the rectangle will help you. So like I was saying, the isosceles triangle, sometimes a property of a rectangle doesn't apply to a question directly. You may have to use some of it, but it doesn't get you straight to the answer. Then you may have to use triangles to help you. So for example, in this one, I have A, B, C, D, and you guys are naming a quadrilateral or any polygon. You pick one corner, and then you go clockwise or counterclockwise, but usually clockwise. You go all the way around the shape in order, listing the letters. You don't want to just randomly zigzag and put the letters. That'll mess up what the sides are when they're trying to tell you where the information goes. So for this one, we have a rectangle, ACB. So to create this angle, I have to draw one diagonal. This angle is 38, and I want to find BAC, which is right here. Now remember the properties of a rectangle. If you have opposite sides are equal, opposite angles are equal, consecutive angles are supplementary, the diagonals bisect each other, and the full diagonals are congruent. None of those properties directly answer this question, because I know that these are opposite each other, but they're not the full opposite angle. When they're talking about opposite angles being congruent, they mean the full angle C and the full angle A are equal. We don't know what the relationship is between the x and the 38 there. We can't say that they're equal, because they're not the full angle. So instead, what we're going to do is think about, okay, this is a rectangle, so I know that this corner is 90. So instead of using one of the properties, I'm going to use the definition of the rectangle to put this here, and I'm going to focus on this triangle. I can use the triangle sum theorem, 90 plus 38 plus x equals 180. And then when you solve that way, you get 52. Right, so that's just one example. There will be others, but you guys have to use triangles, like the definition with the 90-degree corner, to help you instead of a property. Okay? All right, this next one, we have x, y, z, w is a rectangle. The diagonals intersect at O. XO is 12, and YW is y squared minus 5y. Okay, so this is obviously working with diagonals, so we have to think about what we know about diagonals. So we know two things for a rectangle. We know the parallelogram property that they bisect each other, and then the fact that this is a rectangle also adds on the fact that the full lengths are equal. So looking at this one, I noticed that they gave me this full diagonal, so that's a good foundation, but they only gave me part of this one. So I'm going to be using both of the properties. I'm going to use the fact that this was bisected, so if this is 12, then this has to be 12, so the whole thing's 24. Then I'm also going to use the fact that they're equal to each other. So if the full diagonal here is 24, that's going to be equal to this full diagonal, which is y squared minus 5y. Okay, so clearly when you guys see the y squared and the y and then a constant, you're going to have to factor. So I'm actually going to pull the 24 over here so that it's written in standard form, because I'm going to need to factor. All right, and then to actually factor, I want two numbers that multiply to get negative 24. Oops, I don't know why I wrote 2. And add to get negative 5. Those two numbers are, I'll let you think, negative 8 and 3. Alright, so those two multiply to get negative 24, but add to get negative 5. So when I solve, I get positive 8 and negative 3. Now, you want to make sure that you check your answers like we've done in the past with factoring. You want to make sure that you plug in the numbers so that they're positive and they make sense. So when you plug in the 8, you get 64 minus 40, which is 24, which you want it to be. And then when you plug in the negative 3, you get 9 plus 15, right? 9 plus 15, which is 24 again. So that means both of these numbers are going to work for you, and so you're good to go. But always make sure that you double check that the numbers make sense, both that they turn out positive and that the number that you want them to be compared to the other diagonal. Okay, a couple more examples with the rectangle. Alright, so a rectangle is shown. QC is 2x plus 1. QR is 8. TC is 3x minus 1. And I'm trying to find the length of RS, which is right here. I'm going to call that Y just because we already used x. So somehow we have to figure out how to get this information to work together to find that. So what I'm going to do is I'm just going to focus on the two expressions that have x in them and see what relationship I can get from those. So these two segments right here have the x, and if you remember with a rectangle, taking that fifth property and the sixth one that we wrote on the previous page, when you combine them together, because the full diagonals are equal and they've been bisected, all four of these little segments are equal, which means that 2x plus 1 is equal to 3x minus 1. So you can just write that. If that doesn't click right away, you could also say, okay, well, they're bisected. So you could technically put another 2x plus 1 here, because those are equal. You could put another 3x minus 1 here, because those are equal. Then you can add them and set them equal to each other. So you can still use the full diagonals are equal by kind of filling in the missing information, or you could just go straight to those two being equal. You'll get the same answer. But when you solve, you get 2. So basic algebra to get there. So now that I know that x is 2, I'm going to go ahead and plug it in to what I know. So I know that since x was 2 in those expressions, when you plug them in, you'll get 5. So each one of these little segments is 5, okay, when you plug in x. So now I need to figure out how to use that information to find y. So y is right here. I do not know the opposite side, so I can't use opposite sides or congruent. And there's no other real relationship between the sides except for the opposite sides being congruent. So again, when a property doesn't immediately address your question and help you, you're going to be focusing on triangles. So how would you use a triangle to help you find a side? Well, when it's a right triangle specifically, like we have in a rectangle, you're going to be using Pythagorean theorem. Okay? So when your properties aren't going to help you out, look for the triangles. They'll help you. So I have a right triangle here where one of the legs is y, the other leg is 8, and the hypotenuse is 10. So using Pythagorean theorem, you'd have y squared plus 8 squared equals 10 squared. That is a Pythagorean triple, but if you don't recognize that, you can do the Pythagorean theorem, and you get that y is 6, I believe. Yep. Okay? Right, now over to this one. So I know that angle 1 is 30, and I'm trying to find angle 2. I'm just going to call that x, so it's not confusing. All right, so again, I don't really have any properties of a rectangle that helps me out. I don't have opposite angles. I don't have consecutive angles. Those are really the only two things I know about angles. So what I'm going to be doing is using the diagonals instead. They've drawn those on purpose. They've helped us create these two angles. So I'm going to use the diagonals. And remember, like I told you guys when we first introduced that new property, was that because the full diagonals are equal and they bisect each other, I have those 4 congruent segments, which give me isosceles triangles. So this isosceles triangle in particular is what I'm going to be working with. Because these two legs are equal, these two base angles are equal, so I can use the triangle sum theorem to find x. I have 2 x's plus the vertex angle. All those should add up to 180. So if you subtract the 30 and divide by 2, you get 75. Excuse me. Right? And then this one, I know that this angle is 57. I'm going to call this x. It's easier. Again, we saw a question like this at the start of the lesson. I know these are across the shape from each other, but we would not call those the opposite angles like we have in the property. That's referring to the full angle here compared to this full angle, so we can't just say that x is equal to 57. Okay, it doesn't work that way. They're not consecutive. I don't have any other relationships with angles, so again, I'm going to be using a triangle. This triangle right here is the only one that has both 57 and x in it. And by definition of rectangle, that one's 90. So just like we did in that first question, I'm going to be solving this using the right triangle. So x plus 57 plus 90 equals 180. You guys are used to doing the triangle sum theorem, so you guys can do that math. You would get 33 after doing that. And then this last one, I know that angle 5 is 16. Again, I'm trying to find this angle right here. There's no direct relationship between those two using the properties. So I'm going to use the diagonals to help me. So again, I have another isosceles triangle. This obtuse one right here. So if this is 16, I can move the 16 over here. And then again, I can use the definition of a rectangle. This full angle right here is 90. And I just shifted the 16 over closer to that angle. So these two together are complementary. They both add to the 90 degrees. So the x and the 16 together, once I move it over, equal 90. And so if you do that, you get 74. Okay? So that's how you guys will work with your rectangle. Again, look for triangles wherever they're helpful. And remember that extra property is that the full lengths of the diagonals are congruent and the corners are 90 degrees by definition. The next shape we're going to talk about is a rhombus. I don't know how familiar you guys are with this one, but the definition is a parallelogram with 4 congruent sides. So the rectangle has the congruent angles, this one has the congruent sides, okay? So again, it's a parallelogram, so everything that we've learned about a parallelogram is true. I'm not going to make you write all that out again. So just for this one, 1 through 5, all properties of parallelograms. Again, the sides are parallel, the opposite sides are congruent, opposite angles are congruent, consecutive angles are supplementary, and diagonals bisect each other. Those ones that we learned on day 2. A rhombus has 2 extra ones, and this is exclusive from the rectangle, that one that was highlighted for the rectangle, that's for the rectangle. It's not true for a rhombus, okay? The rhombus has its own 2 separate new ideas here. So the first one is that diagonals are perpendicular. Diagonals are perpendicular. So that means that where the diagonals cross inside of the rhombus, they do create for a 90-degree angles on the inside. The corners are not 90 like a rectangle. It's where the diagonals meet. And then diagonals bisect opposite angles. So essentially the angles that the diagonals slice through, the opposite ones, because they're going from one corner to the next diagonally like this, those 2 angles that they touch, they divide in half. So I'll draw a quick illustration of that. Remember a rhombus, all the sides are the same? Okay, so when you draw, I'm not going to draw both diagonals because it'll get a little bit messy, but when you draw a diagonal, it splits those angles in half, the opposites. Now this is kind of like a rectangle. Remember how for a rectangle, the full diagonals were congruent and they were bisected, so all 4 segments were equal. But well, in here, remember that the opposite angles are congruent and they've both been bisected. So each one of these 4 halves, all 4 of them are equal. Okay? So those 2 ideas with the full things being equal and them being bisected, with those 2 working together, it gives you 4 things that are all equal to each other. And that's true for the other diagonal too. I just don't want to make the illustration messy, so I'm just going to draw one. But it is true for both. All right, so let's use these properties to help us solve a rhombus. Now the same thing applies for a rhombus. If a property does not immediately apply, you can use the definition of a rhombus and the triangles inside to help you solve. So this one, we have ABCD is a rhombus. Find the measure of BAC, which is right here. So for this one, I am going to use a straightforward property. So this one, the property I'm going to use is the fact that the diagonals bisect opposite angles. So I know that this angle has been bisected, and I know this angle has been bisected. Let me draw that a little bit bigger. Okay, but I also know, together with the idea of the full angles being congruent, I know that this full angle C is congruent to this full angle A. So all 4 of these halves are the same, just like I was describing in that earlier diagram. So that means that x is 41. Okay? If this is equal to this and they've both been cut in half, then both halves are equal. That's one way to do it. There are a lot of different ways that you guys can approach these questions, especially with a rhombus. Another way that you can do it is that you can use the definition of a rhombus. The definition of a rhombus says that all 4 sides are equal. So when you guys look at half a rhombus, that's an isosceles triangle. Isosceles triangles help you with a rhombus too. They just are in different positions than they would be in a rectangle. So half of a rhombus is isosceles because these 2 sides are equal. And so those are the base angles, so they're equal to each other. Okay? You could also, here's another one, you could also do, because these sides are parallel, if this is x, you can shift the x down here, right, because they're parallel, those are alternate interiors, so you can shift the x down, and if this angle has been bisected, then both halves are equal, making it 41. So there are a lot of different ways that you guys can use a rhombus to solve for answers. Just find the one that kind of clicks with you first. All right, this next one, again, they haven't named it, so I'm going to put the letters in. Angle O is 112. LKM, so I need to draw a diagonal. This angle right here is what I'm trying to find. So again, see if we can use any properties of a rhombus. So I have one diagonal here, and I'm looking for this right here. I know that the diagonal bisects the angle, so if I know that's x, this is also x. Okay, and again, there's a lot of different ways you can do this, but once I put this x here, I notice that this full angle is 2x, and this angle is 112, and they're consecutive. So this full angle K and this full angle O, they're consecutive angles, and in a parallelogram, which a rhombus is, they would be consecutive. So I can do 2x plus 112 is equal to 180, and solve for x that way, which would give me 34. And again, there are other ways you can do this. You could use alternate interior angles to put the x here. Right, you can put the x there, and then you could put this x here too, and then do isosceles triangle again. And all the sides are equal, so you could do another isosceles triangle with the 112 as the vertex angle and solve that way. There are a lot of different ways that you guys can do it. All right, this one, rhombus. PRTS has diagonals that meet at O. RPO, which they've provided for us already, is that value. They want us to find PRS, x, right here. So again, let's see what we know about a rhombus that can help us. So I have the diagonals in here. You could use the definition of a rhombus like this. I could say, hey, look, this is an isosceles triangle. The diagonal has been cut in half, so there's another x right there. Because this is isosceles, this is 57. And then you can use triangle sum theorem. 57 plus 57 plus 2x equals 180. It's one way. That's using the bisecting, the diagonals bisect to get both of those equal, and then the isosceles idea. You could also remember that another property of a rhombus that's easy to forget but very useful is that the diagonals are perpendicular. Okay? When you know that the diagonals are perpendicular, this little guy right here, this fourth of a rhombus, is a right triangle. So you can focus on the smaller triangle to find x using the triangle sum theorem that way too. Whatever method you guys use, the bigger isosceles triangle with half a rhombus, or just the smaller one here, you should get the same answer either way. And so that answer is going to be 33. 57 plus 90 plus x equals 180 and solve. But any way you guys do it, you should get that number. If you prefer just automatically, if you prefer just automatically doing this every time and try to get the isosceles triangle to work, that often works most times. But again, if you more succinctly just want to put that one angle in there and focus on the smaller triangle, that works too. Okay? There are a lot of different ways. As long as you use a valid method, you're good. All right, next one, put the letters in. This side is 7x, this side is 3x plus 10, this side is y. Alright, so again, avoid mixing variables when you can avoid it. So I'm not going to use this to try to find the x's. I'm going to see if there's a relationship between these two. Because this is a rhombus, by definition, all four sides are equal. So I know in a parallelogram, opposite sides are equal, and that's still true here. So in a second, I might be able to use this side to help me find y. But not only are the opposite sides equal, the adjacent ones are too, because all four of the sides are equal. And that's true for a rhombus, not a rectangle. Our definition of a rhombus says that all four sides are equal. That's not true for a rectangle. But for this shape, because of that definition, I can say that these two sides are equal, not just the opposite ones. Okay? So when I solve that, I would get x equals 2.5. Yeah, 2.5. And so once you find x, there are two ways you could find y. You could plug the x in here, and because they're opposite sides, or just because all sides of a rhombus are equal, once you know this, you can find that. Or you can plug it into this one, because that's easier. So 7 times 2.5, those are also going to be equal by definition of a rhombus. And so either way, you should get 17.5. All right, a couple more of the rhombus before we go on to the square. So this one here, I know the perimeter of the rhombus is 68. So remember, the perimeter is all the sides added together, and what's helpful with the fact that it's a rhombus is that all four sides are equal. So I can manipulate the perimeter to help me. If I know that all of them added together is 68 and they're all equal, I can divide by 4 and find each of the sides individually. You can't do that if you don't know the sides are all equal, but if the sides are all equal, you just slice it into 4 pieces. I also know that this side is 8, and I'm trying to find this. Okay, so in a rectangle, if I didn't know the outside sides, we do have that property in a rectangle that all 4 of these are congruent, but that is not true for a rhombus. That extra property that we learned for the rectangle doesn't follow through for a rhombus. So for the diagonals, I can't just say that 8 is equal to x. I know you guys might be tempted to say that because it's easy. But that property we were just talking about for the rectangle does not apply for a rhombus, so we have to think of something different. So we're not going to be able to use the diagonals to help us because this diagonal has no relationship to this one except for the fact that it cuts it in half. So we have to think of something different. So the property that we're going to use, okay, so we are going to use the diagonals, but not their lengths. The other property that we know about a rhombus with its diagonals is that they're perpendicular. Again, a very easy property to overlook, but a very crucial one. So the fact that they're perpendicular gives me a 90-degree angle here, which indicates that this triangle right here, which I'm going to redraw, this triangle is a right triangle. And when you have 2 out of 3 sides in a right triangle, the way you find the third is Pythagorean theorem. So 17 squared is equal to x squared plus 8 squared. Oh, that's 15. That's also a Pythagorean triple. Not one I had to memorize, but it is one. So when you solve the Pythagorean theorem, x is 15 after you do that work. Okay, so again, don't overlook that property of the diagonals being perpendicular. It may just be the thing you need to move forward. So when you guys are super stuck and you're not sure what to do, think about those extra properties of a rhombus, the diagonals bisecting the angles and then the diagonals being perpendicular. They may be exactly what you need to move forward. All right, these last two really quickly. I know that, oh, okay, there are no letters. B, A, C. I don't know, I didn't put the letters in there. But BAC, that angle there, the 28 is, sorry, yeah, the angle marked 28. I'm going to use that to try to solve for x. So there, again, lots of different ways to do this. You guys could, again, use the fact that the diagonals are bisecting the angles. So you could say this is 28, right? But then because opposite angles are equal, then each of the halves, all 4 of those halves should be equal. So that makes the x 28 automatically, right? You could also do this. I think one of my students saw this really quickly. Because it's a parallelogram, the sides are parallel. So alternate interior angles gives you x equals 28 too. Whatever you guys see first, however you want to manipulate the picture. It doesn't matter if it's the short way or the long way. As long as it's valid, go with what you see in the picture. And then lastly, the measure of angle A is represented by this expression I want to solve. So angle A is right here. So this uses the property of the diagonals being perpendicular. There's no other way to solve. So that angle, all 4 angles in here are 90. So I do 16x plus 6 is equal to 90 and solve. And I would get 5.25. Okay, so there's your rhombus. Don't mix up stuff from the rectangle with stuff from the rhombus except for what they have in common, which is the parallelogram stuff. Make sure that you keep the information about the rectangle separate from the rhombus. Extra stuff like the diagonals being perpendicular and the diagonals bisecting angles. It's very important that you keep them separate. Otherwise, if you try to use a property for a shape it doesn't belong to, obviously you're not going to get the right answer. You're not going to understand how to actually approach the question. All right. Last shape we're going to talk about before we get into those proofs. So a square, I'm sure you guys are most familiar with this. You guys probably know a lot about a square. So a square is a parallelogram with 4 congruent sides and angles. So what's cool about a square, and I did introduce these shapes in a particular order on purpose, A square is a rectangle and a rhombus. It's kind of like they're kind of mushed together. So the rectangle had the congruent angles, the rhombus had the congruent sides. When you put them together, you get a square. So a square is both a rectangle and a rhombus, as well as being its own category, a square. So just kind of think about how the Venn diagram would work with the rhombus, the rectangle, the square all working together. It's basically, well, since I brought that up, all right, rectangle, rhombus, square. Okay, so there's a way you can kind of look at that as a Venn diagram. All right, but the square is really nice because a square is both a rectangle and a rhombus. Literally everything that we've talked about up to this point is true for a square. So you don't have to worry about anything new that's being added on, and you don't need to worry about accidentally using a property that you're not supposed to for a square, because everything that we've learned so far is true about a square. So properties, everything well, I don't know how to say it, but everything we know so far. I started in all caps, but that took too long, so I switched. Right, so everything that we know so far is going to be true about a square. Everything about a parallelogram, everything about a rectangle, everything about a rhombus. You don't need to worry about anything new, and you don't need to supposed to. Okay, so first question, we're going to solve for y in the square below. So remember, we're just working with this angle right here. So because a square has 4 congruent angles, the same way that a rectangle does, this is 90 degrees. I'm sure you guys know that with a square. All right, so we know that y squared minus 13y equals 90. Again, another situation where we have to factor. So we're going to pull the 90 over so it's in standard form. Two numbers that multiply to get negative 90 but add to get negative 13. It's going to be negative 18 and positive 5. We're going to get those two numbers by setting the factors equal to 0 and solving. And then remember to double check that they make sense. So if you plug in the 18, if you do 18 squared minus 13 times 18, you get 90, so that checks out. And then if you do negative 5 squared is 25 minus 13 times negative 5, also 90, so they both check out. So both of those values are going to be your answer. All right, next one. We have a square here. I know that this is 5x plus 2y. AD is 3x minus y, and BC is 11. I want to find the value of x and y. So again, you can see how the x and the y have been incorporated into the same expression. So this is going to be a system. We can't avoid it. So with a square, remember the definition of a square is all sides are equal. So that means not only are the opposite sides equal, but the adjacent ones are. But I think it'll be easiest if I just say this is equal to 11 and this is equal to 11. It'll make the equations a little bit neater. So 5x plus 2y equals 11 and 3x minus y equals 11. All right, so you guys should remember how to solve systems. Okay, I'm going to focus on the y. I'm going to cancel out the y. So if I multiply the bottom equation by 2, I can use the elimination method. Those go away. I get 33. So this would give me x is 3. And then remember, when you're trying to find the value of the other variable, you just plug it in. So if I plug that in here, I get 15. Hold on. I don't think I did this one. So 11 minus 15 divided by 2. So y would be negative 2. Okay? So again, systems and factoring, make sure you guys are okay with those. All right, lastly, to prove shapes are, okay. So when you guys are proving things, whether it's a rhombus or rectangle or a square, because they are parallelograms, when you guys are doing proofs, you first need to prove that it's a parallelogram. If you can't, within the proof, get straight to one of the unique properties of these shapes, or even if you can, you need to prove that something is a parallelogram first and then move forward to show that other property working together with a parallelogram. That's how you show that it's actually a rectangular, square, or rhombus. So in these proofs that we're going to see, if they don't already say that it's a parallelogram, you have to show that first, and then use the special properties about those shapes to show what type of parallelogram it is. So just be mindful of that. So this first one, they've given us that BD is a perpendicular bisector. They put all the markings in the picture. So we know BD is a perpendicular bisector, and we know that AD is parallel to BC. So I'm going to go ahead and write the givens. Did I do separate lines? I did. Okay. BD is a, I'm just going to abbreviate that, perpendicular bisector. Oh, there we go. And then AD is parallel to BC. All right, so we have our givens. Now, we are trying to prove, we don't know that this is a parallelogram. They haven't told us that. So in order to prove that it's a rhombus, we first have to show it's a parallelogram and then pick one of those special properties about a rhombus to show that it's not just a parallelogram, it's also, or it's more specifically a rhombus. So looking at what we know, I can see that these two are equal. So this diagonal has been bisected, and then I also know that these are parallel. But that's not enough just up front to say that it's a parallelogram, so I have to think a little bit. So with the perpendicular bisector, I only know that these two are equal and that all of these are 90 degrees. So I'm going to hold off on that because I can get a little bit more to work with the lines being parallel. So I'm going to work with that. So hold on. I'm going to strategize with you. I'm going to brainstorm a little bit before I actually write the proof. So in order to prove that this is a parallelogram, I think that the easiest way to do that is to show that both of the diagonals bisect each other. So I've already got one. I've already got that one has been bisected. If I can show that this is true, then I can say it's a parallelogram because that's one of the properties of a parallelogram. So how could I show that EB is equal to ED? Well, if you look at this rhombus, remember it's been split into triangles. So I'm going to use the triangles to help me. Again, just like in solving, if you don't have a direct property that you can use the triangles. So what I'm going to do is I'm going to see, because it's a perpendicular bisector, if you guys look carefully, I have side, angle, side. I also have side, angle, side. So what I can do is, well, I'm going to use congruent triangles to help me get that these two are equal by CPCTC, that tongue twister, right? I don't currently know that those are equal, that's what I'm trying to get. So I'm going to erase those for a second. I need to figure out what other property I could use besides side, angle, side to prove that those triangles are congruent. And that's where the parallel lines come in. If I can use parallel lines using the Z, so I can use alternate interior angles to say that those are congruent, then I could say that the triangles are congruent by angle, angle, side. And then once I have the triangles are congruent, I can use CPCTC to get that these segments are equal. Then I can use that to show it's a parallelogram, and then you'll see where we go from there. So now that I kind of know what I need to do, I'm trying to get those diagonals to be bisected. I'm going to prove that the triangles are congruent. So first things first, with the parallel lines, I'm going to say that angle ADE is congruent. I need to put the letters in the correct order. So ADE is congruent to CBE. And remember, when you have the parallel lines first and then you're using the angle rules, that's not the converse. So this is alternate interior angles theorem. So use alternate interior angles to get those two to be congruent. And then I had this here, but I'm going to need to put this here as well to get that relationship. So I'm going to say angle AED is congruent to CEB. That's the vertical angles theorem. That says all vertical angles are congruent. So the fact that they're perpendicular, that's cool, but I just want them to be equal for now so I can prove that the triangles are congruent. And then I already have, okay, so with the angle bisector thing, using the angle bisector, I can say that AE is congruent to CE. I didn't have this physically written down yet, so that's why off of this given, I have to physically write that down. That's the definition of perpendicular bisector. Gives me that those two are equal. Okay? So now that I have these angles are congruent, these angles are congruent, and these segments are congruent, I can say that triangle ADE is congruent to triangle CBE by angle, angle, side. Okay? Now that the triangles are congruent, I can get those two segments I was after, this one and this one. I can say that DE is equal to BE because corresponding parts of congruent triangles are congruent. So now that I have that, I have this diagonal has been cut in half and this diagonal has been cut in half. Therefore, ABCD is a parallelogram. You have to do this first, right? Diagonals bisect each other. In parallelograms. Or however you want to, you could use an if-then statement, whatever, however you want to express that to me. So you first have to show me that it's a parallelogram. Then you want to think, what else do we know that's special about this that would tell me in particular what type of parallelogram it is? What is unique here that shows that it's a rhombus instead of just a generic parallelogram? Well, that's where the perpendicular part comes in, because remember for a rhombus, the diagonal is perpendicular. So here you can say ABCD, not only is it a parallelogram from the top, or the previous line, it's a rhombus, and then you can say diagonals are perpendicular in a rhombus. Remember, we knew they were perpendicular from up here. They told us that already. Okay? So this is your proof. I know it's a little bit kind of a brain stretcher because you had to use congruent triangles, which we haven't done in a while. But again, when it's not straightforward, you have to figure out what you need to do to prove that it's a parallelogram first, and then find that special quality that moves it to being a rhombus specifically. So yes, using triangles in different ways. We saw how we use them to help solve. They can help you with your proofs as well. You just need to know how to do that. Okie doke. Oof, this one's a little bit longer. All right. Hang tight, everybody. How long is this video so far? Okay. All right, so this one we have, I don't know why it's called that, but we have what. What is a parallelogram? That's given. And then we have dart is a rhombus. That's given. And what I'm after is to prove that what is not only a parallelogram, it is more specifically a rectangle. So I'm going to trace what in blue, and then I'm going to trace dart in red. Okay, so I need to somehow figure out how to make WHAT, what a rectangle. So let's think about things we know about a rectangle and how I can prove that. I already have the parallelogram part. Right, so remember how I said when you guys are trying to prove something's a rectangle, a rhombus, or a square, you have to prove it's a parallelogram first? They already did that. They gave that to us. So now all I have to do is focus on what can I show in this picture that's unique to a rectangle that's true about WHAT. So the fact that it's a parallelogram, we know that opposite sides are equal. Okay, I'm going to go ahead and put that in. We're just kind of brainstorming, so what I draw, we might erase, but we're brainstorming right now. So I know that these two are equal. I know these two are equal. Remember, in a rectangle, we don't know all four are. We just know opposites. Sorry, it's not a rectangle. It's what we're trying to prove. All we know is it's a parallelogram. Sorry. So we know opposite sides are congruent. I know opposite angles are congruent. I know the diagonals bisect each other. And then I know the consecutive angles are supplementary, but we're not really doing anything with angles. So because it's a parallelogram, the only things I'm working with, excluding the angles, is that the opposite sides are congruent and the diagonals bisect each other. Now, let's move on to the rhombus. I know that in a rhombus, all the sides are congruent. Okay, so I know that. And I only have one diagonal here, so I don't think we're going to be using anything in terms of the diagonals of a rhombus. So I know all four sides are congruent and we're not doing anything with angles. So I think that's where I'm going to stop with the rhombus. So if you guys look really carefully, notice how the way that dart kind of juts into WHAT, these two segments are the only thing that they have in common. This segment right here of the diagonal is one side of the rhombus. So I think I'm actually going to be focusing on the diagonals of what instead of the opposite sides. So I'm going to erase those. That was a good brainstorming technique, but I don't think I need those anymore. What I'm going to focus on really is the diagonals. So I know that these are going to be equal, right? And these are going to be equal. I'm just going to do that so we can see. So hopefully you guys can kind of see where we're heading with this. Since I'm trying to prove that WHAT is a rectangle, what's unique about a rectangle with its diagonals is that the full lengths are equal. So I think what I'm going to try to do is show that this full diagonal is congruent to this full diagonal using the rhombus to guide us. Okay? So the first thing I'm going to do is I'm going to say that DA is congruent to DT. Those are the two parts of the rhombus that are inside or that the parallelogram and the rhombus have in common that are overlapping. And I know that they're equal. That's the definition of rhombus. The definition of the rhombus tells me that those two are equal. Okay? The next thing that I did when I noticed that I was focusing on the diagonals was use that property of a parallelogram. So I'm going to say that DH, I put them in a particular order in my notes, that's why I'm looking really carefully. DH and DT are congruent, and just to save space, I'm going to put them both on the same line. DW is congruent to DA. Start them all with D. Alright, so I said that that was bisected, that diagonal is bisected, has two congruent parts, same thing with the other diagonal. And so that's diagonals of parallelograms are bisected, or sorry, bisect each other. Okay, so this is what we got so far. Now, if you look really carefully, see how I have DT twice? What I'm going to do now is I'm going to use substitution. Sorry, hold on. Alright, well I have DA and DT twice, so I'm going to do substitution with both of these, but in a strategic order. So I'm going to say that DW equals DT. I'm going to use this guy, I can circle it here. I'm going to use this one. So DW, I'm going to switch that out for the DA up here. I have this. So I now know that DW is equal to DT. So those two are going to be equal. That's what I know so far. And that's substitution. So I use the bisecting of the diagonals to start manipulating the picture to show that different parts are congruent. Now what I'm going to do, now this, depending on how you guys write your own proofs, this may not be a logical sense for you, but again, proofs are hard to teach because different people see logic flow in different ways. But the way that I saw this logic flowing was after I did this relationship, I now need to switch into the segment addition postulate. So again, because you're trying to prove that the full diagonals are congruent, so I'm going to start defining the full diagonals with the segment addition postulate. So I'm going to start with TH. So TH with the segment addition postulate is equal to DT plus DH. Segment addition postulate. I'm going to start with that. Okay? Now, I know a relationship between DT and DH, which is right here. So what I'm going to do is I'm going to say TH is equal to DT plus another DT because DH is the same thing. So that's two DTs. Another substitution. Sorry, I'm writing so low on the board. Alright, so I decided to switch the DH for the DT so I can have the two DT right there. And the reason I'm doing that is because DT is that side of the rhombus. I'm going to focus on that. Right, I'm going to do the exact same thing for the other diagonal, AW. AW is equal to DA plus DW. Right, that's just a straightforward segment addition postulate. Now I need to manipulate this a little bit more. Right, so I'm going to say AW is equal to, Okay, so this one is a little bit more complicated. So I have the dA and the dW. I could do dA plus dA or dW plus dW and do it that way. But remember, I'm trying to somehow get the relationship of a W and TH to be the same. So I somehow want to make sure that they're using the same segment over and over again. So for TH, I've already said that this is 2 times dt. So if I can somehow say that this is also 2 times dt, that would get the commonality of those diagonals, that they would both be equal to the same thing. So let's see if I can do that. Is dA equal to dt anywhere? Yes, it is. So instead of writing dA, I can say dt. Is dW equal to dt anywhere? Yes, it is, right here. So I can go ahead and switch this out and write 2 dt. So now you guys can see I reduced I changed the expression of the full diagonal to be the same for both. Okay, and so this was substitution. I know that's a little bit more abstract than we're used to for substitution. We're used to just switching one out, but I switched both out so that I am using the same variable for both. I might need to scroll up, which means I need to erase things, but hold on. Yeah, I'm going to need to erase. So just remember that last step with the substitution. Scroll up. I don't know what line we were on. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm on this one, I think. Alright, so now that we know that TH and AW are equal to the same thing, I can say that they're equal to each other. That's another substitute. We use so much substitution. Alright, so I used the fact that I had all sorts of individual little pieces that were equal to each other, and I manipulated that in a way to get the full segments, or the full diagonals, to be congruent. So now that the full diagonals are congruent, and I already have that it was a parallelogram, I can finish by saying WHAT is a rectangle. I didn't even have to use all the lines here. Alright, WHAT is a rectangle, and we got to that conclusion because we said that the full diagonals were congruent. So we would say full diagonals are congruent in a rectangle. Okay, so believe me, I know anytime you guys use segment addition postulate, it makes the proof like 20 times more difficult to understand. But when you guys have little pieces all separated and you need to link them together to have a relationship, almost always you're going to be using segment addition postulate. So you guys need to get familiar with that again and how to use that. Again, the proofs that you guys are going to be doing, it's a wide variety of difficulty. Some of them are more straightforward, some of them aren't. Just get used to seeing the different types of proofs and look up practice. They have a lot of practice that you can find with these kinds of proofs in particular that you can look up, and I'll try putting some on Blackboard too that you guys can experiment with. But again, segment addition postulate, I know it's complicated, but if you recognize that you have a bunch of different segments that you need to pull together, that's what you're probably going to be doing.